Good morning everyone. Today I am here to give seminar on topic finite state automata. Finite automata. Many string matching algorithms build a finite automata, a simple machine for processing the information that scans the text string T for all the occurrence of the pattern P. But these string matching automata are very efficient because they examine each text character exactly once, taking the consistent time per text character. The matching time used after pre-processing the pattern to build the automata is therefore theta of n. Now I define what is finite automata. Finite automata can be denoted as with the m, which is a phi tuple represented as q, q naught, a, summation delta, where q is the finite state set of states and q naught belongs to q, which is the starting state, and a is a subset of q, which is a distinguished set of acceptable states, and summation is a finite input alphabets, where delta is a function from q into summation into q, called the transition function of m. This is a simple two-state finite automata with the state set q equal to 0 and 1, and starting state q not equal to 0, and input alphabet summation equal to a comma b. Then this figure from the a shows that tabular representation of the transition function delta, whereas figure b shows the an equivalent state transition diagram, that is state 1 shown back end, is the only accepting state. Directed edges represent the transitions. For example, the edge from the state 1 to state 0 labeled to indicate that delta of 0 comma b equals to 0, that is it moves to the it is in the initial state 0. This automata accepts those strings that end in the odd numbers of a's, that is if a given input is a, then it moves from the initial state, that is 0 to 1. If the given input is a and b, then it moves from 0, first it moves from state 0 to 1 and then from state 1 to 0, but this is not acceptable. If the given input are a b a and ba, then this is not acceptable. This is because if initially it moves from 0 to 1, that is a, then from b, if it receives the b input, then moves from 1 to 0, again it receives the b, means it is loops there only, that is in stays in the state 0 only. If we when it accepts the a input, then it goes to the state 1, and again if it receives the a input, then goes back to the 0 state, that is means it is returning the initial state again, therefore it is not acceptable. The given input is like a b a and a, then it is acceptable because it is ending with the 3 a's. First initially is accepting the a input. A means it moves from 0 to 1, that is a. Then if it is accept the b, means it is going from 1 to 0 state, that is b. Again it accepts the a, means it is moving from 0 to 1, and again a means 1 to 0, and one more a means 0 to 1, that means it is reaching the final state 1. This is acceptable. The finite automata begins in the state q naught, that is starting state, and reads the characters of its input string one at a time. If the automata is in the state q and reads the input character a, it moves from the state, that is q, to the state delta of q comma a, that is moving from the initial state to the next state with the input a. And whenever its current state is q is the member of a, that is accepting states, then the machine m has the accepted the string and that is read so far. An input that is not accepted is rejected, as I explained in the above example. A finite automata m induces the function that is called final state function from summation star to the q, such that phi of w is the state m ends up in after scanning the string w. Thus the m accepts the string w if and only if phi of w belongs to a. We define the phi function recursively using the transition function that is written as follows, that is phi of epsilon equal to q naught. Q naught is a starting state, and phi of w of a equals to delta of phi of w comma a for all W belongs to summation star, A belongs to summation. Here W indicates the string matching automata. In string matching automata, for a given pattern P, we construct a string matching automaton in pre-processing steps before using it to search the text string. The automaton for the pattern P, that is A, B, A, B, A, C, A. What we assume here is that P is a given fixed pattern string. For brevity, we shall do not indicate the dependency upon P in the notation. In order to specify the string matching automaton corresponding to the given pattern P, that is 1 to M, we first define an auxiliary function called the suffix function corresponding to the P. The function, that is sigma, maps the summation star to the summation star to 0 to 1, such that sigma of x is the length of the longest prefix of the pattern P, that is also suffix of the x. Therefore, how we write it is as sigma of x equal to max of k colon pk is a suffix of x. The suffix function sigma is well defined since the empty string p naught is equivalent to epsilon is a suffix of the every string. As an example, for the pattern p equal to ab, we have sigma of epsilon equal to 0. This is because given the pattern, if given pattern is a b a b a c a, therefore it is matching the first prefix of the given string, that is suffix of the given string, that is ab matches the prefix of the given pattern pa, therefore it will be 0. In second, if the given string is like sigma equal to ccaca, it goes to the first state, it equal to 1. This is because the prefix of the pattern matches the suffix of this given string, that is given pattern will be a b a b a c a, then last suffix of this string matches the prefix of the given pattern, that is first pattern a of a character, therefore it will be 1. And for example, if one more example, like a string is given like ccab, then move to the second state. This is because the suffix of the string, that is ab, matches the prefix of the given pattern. I will show it in the figure. For pattern P of the length m, we have the sigma of x, that is equal to m if and only if P is a suffix of x. From the definition of the suffix function, x is a suffix of the y implies sigma of x less than or equal to sigma of y. We define the string matching automata that correspond with the given pattern, that is P of 1 to m, as follows. That is the state set, that is q is the 0 to m. The starting state will be q naught is a state 0, and the state m is the accepting state, that is the final state. The transition function delta is defined by the following equation for the state q and the character a as follows. That is delta of q comma a is equivalent to sigma of pq of a. This is the one more example with 8 states with the pattern a, with the input pattern like a b a b a c a. In this case, this is the transition diagram for this pattern, and this is a tabular function, tabular representation for the given pattern with 8 states with input a b c. These are the indexes used. Once the pattern matches, that will be shaded. From the above example, A is the from the above figure. This is the transition diagram. What it indicates is, and the transition diagram for the string matching automaton that accepts all the string ending in the string A, B, A, B, A, C, A. And the second one, the corresponding to the transition function delta, and the pattern string P equal to A, B, B, A, B, A, C, A. The entries corresponding to successful matches between the pattern and input character are shown shaded, that is shown in this table. Here shaded, that is 1, that matches A will be matched, then it will shaded as shaded here, then B matches, that will be shaded here, then if C matches, again A matches, then it will be shaded here, again B matches, it is shaded here, if C matches, here it is shaded here, and so on. And then this that is C. This C indicates the index number with the index number, as well as the operation of the automaton on the text T equal to this given pattern, that A B BA, BA, BA with CA and BA. Under the each text character TF, TR, TI appears the state phi of TI, and that automaton is in the after processing the prefix of TI. The perfect match found at the position 9, that is shown here. This is the finite automata matcher. This is finite automata matcher. The algorithm for finite automata matcher is this: the n equal to t dot length, that is the text length, q equal to 0, that is initial state, and for it loops for I equal to 1 to n. Then in fourth line, q equal to delta of q comma ti, that is the text of the given pattern. If the initial state equal to final state, that if the given string matches the pattern, then pattern occurs with the shift, that's I minus m. To clarify the operation of the string matching automata, we now give the simple efficient program for simulating the behavior of the such automata in finding the occurrence of the pattern p of the length m in an input text, that is t of 1 to n. As for any string matching automata for pattern of length m, the state set, that is q, is 0 to m. The starting state will be 0, and only accepting state is that is final state will be m. From the simple loop structures of the finite automation matcher, we can easily see that its matching time on the text string is of length theta of n. Consider how the automata now we consider how automata operates on an input text, that is t of 1 to n. We shall prove that the automata is in the state sigma of ti after scanning the character t of I, that is text. Since the sigma of ti equal to m if and only if pattern is a suffix of the text, that is ti, the machine is in this accepting state m, that is final state m, if and only if it has just scanned the pattern p. To prove this result, we have to use the following two lemmas about the suffix function sigma. There are two lemmas used. First one is suffix function inequality, and second one is suffix function recursion lemma. Let us move to the first one, suffix function inequality. In suffix function inequality, for state that for any string x and character a, we have that sigma of x a equal to r, that is less than equal to sigma of x plus 1. This is the by looking at this figure, let we denote that r equal to sigma of xa. If the r becomes 0, then conclusion is that r equal to sigma of xa, that is equal to r is less than or equal to sigma of x plus 1, is trivially satisfied by non-negative of sigma of x. Now we assume that if r is greater than 0, then pr is the suffix of xa by the definition of sigma. Thus what we prove is pr minus 1 is the suffix of x by dropping the a from the end of the pr and from the end of the xa. Therefore r minus 1 is less than equal to sigma of x. Since sigma of x is the largest case such that pk is the suffix of the x, and thus sigma of xa equal to r is less than or equal to sigma of x plus 1. Next one, suffix function recursion lemma. In this recursion lemma states that for any integer x and character a, if the q equal to sigma of x, then sigma of xa equal to pq of a. This is the figure shown for the suffix function recursion lemma. Proof states that from the definition of the sigma, we have the pq is a suffix of the x, as shown it is in figure. We also have the pq is a suffix of xa. If we let that r equal to sigma of xa, then pr is a suffix of xa, and by the above lemma, that is suffix function inequality lemma, what it says is r is less than or equal to q plus 1. Thus what we have is magnitude of pr is equal to r is less than or equal to q plus 1, that is equal to magnitude of pq of a. Since pq a is a suffix of xa and pr is a suffix of xa, and hence we have pr is less than or equal to pq of a. The lemma implies that pr is a suffix of pqa, therefore r is less than or equal to sigma of pqa, that is sigma of xi is less than or equal to sigma of pqa, but we also have sigma of pqa is less than or equal to sigma of xa. Since pqa is a suffix of xa, thus we have finally we have that sigma of xa is equivalent to sigma of pqa. Here is one more theorem is there. If pi is the final state function of the string matching automata for a given pattern P and T of 1 to n is an input text for the automata, then pi of Ti equivalent to sigma of Ti for I equal to 0 to n. The proof said that can be proved by induction on n, that is for I equal to 0, then theorem is trivially true. Since T0 is equivalent to epsilon, thus pi of T0 equal to 0, that is equivalent to sigma of T0. And then now we assume that the pi of Ti equal to sigma of Ti, and we prove that pi of Ti plus 1 equal to sigma of Ti of I plus 1, that is now we assume that pi of Ti equal to sigma of Ti, and we also prove that pi of Ti plus 1 is equal to sigma of Ti plus 1 by denoting the pi of Ti, and let denotes the Ti of plus 1, and let A denotes the Ti of plus 1. Then we have that pi of Ti of I plus 1 is equivalent to pi of Ti A by the definition of Ti plus 1 and A, and that is equivalent to delta of phi with the Ti comma A by definition of phi, and delta of q comma A by the definition of q, and sigma of pq comma A by the definition of delta, and sigma of Ti comma A by the lemma and induction. Then finally we have that pi of Ti of plus 1 is equivalent to sigma of Ti plus 1 comma A, because the definition of the Ti plus 1. Computing the transition function. Now I am going to explain the computing transition function. This is because in earlier finite automata matcher algorithm, it does not include the pre-processing time required to compute the transition function delta. So that can be solved here by this algorithm. Initially m equal to p dot length, that is pattern length, and q equal to 0 to m, that is start with the state 0 to the accepting state m. For each character, that is a belongs to summation, that is accepting inputs, k equal to minimum of m plus 1 comma q plus 2, and then this loop will be repeated until k equal to k minus 1, and until it will be pk becomes a suffix of the pqa, and delta of qa equal to q, then return the function delta. The procedure computes the transition function delta from the given pattern, that is p of 1 to m. This procedure computes the delta of q comma a in the straightforward manner according to its definition in the equation. The nested loops begins on the line 2, and line 3 considers all the state q and the character a, and the line 4 and 8 set delta of qa to be largest k such that pk is a subset suffix of pqa. This code starts with the largest considerable value of the k, which is minimum of m comma q plus 1. It then decreases the k until the pk is a suffix of the pqa. It must eventually occurs since p not equal to epsilon is a suffix of every string. The running time of the compute transition function is the order of m cube magnitude of summation, because the outer loop continues a factor of m, that is magnitude of summation. Then the inner loop can run at most m plus 1 times, and the test for the pk is a suffix of pqa, and the line 7 can require comparing to the m characters. With the improved procedure for computing delta, we can find that all the occurrence of the length m pattern in the length n text over an alphabet summation with this order of m magnitude of summation, pre-processing the time and theta of n matching time. Thank you.